In this video, we're going to discuss Lewis structures of ions. So if we have something like S2-, a sulfide, well, our sulfur would have 6 valence electrons. But S2- has 2 extra electrons. That's what gives it the negative charge. So we'll use X's to indicate the extra electrons. I have to put 2 more electrons on it. And so what does S2- look like? It looks like a sulfur with 8 electrons around it. If I go and make something like SO4 2-, a sulfate. Well, at first, sulfur followed by 4 atoms. It's probably a sulfur in the middle and 4 oxygens around it. We'd put the 6 electrons on each. Eventually we have all the electrons on our atoms. But that's not all the actual electrons. We put the normal valence electrons for when it's neutral. I have 2 extra electrons. They have to go on this molecule. Where do they go? As a general rule, we put them on the more electronegative atoms. These are almost certainly the outside atoms. So I have 4 oxygens. These are definitely more electronegative than sulfur. They're further up in their column. But there's 4 of them and I only have 2 extra electrons. I can pick any 2 I want. And so I'm just going to put one here and one here. Now, you don't want to put them on the same atom, as that would put a lot of extra charge on a spot. That is an extra electron. It's an extra negative. Easier to have only 1 extra negative on an atom than to have 2. And so at first we spread them to there. We then go and pair unpaired electrons. And, well, because of the extra electrons, the right and left oxygen only need to bond once. My bottom oxygen and my top need to bond twice, and sulfur doesn't have any more unpaired electrons. Sulfur has to break up its lone pair, and then the oxygen can bond. Same with the top. It can break up its lone pair, and then the oxygen can bond to the now unpaired electrons. What you end up with is a sulfur with a double bond up, a double bond down, a single bond left and right. But those oxygens left and right, because they had the extra electron, end up with 3 lone pairs, while the top and bottom oxygens only had 2 lone pairs. Because we put the extra electrons on the oxygens, they are negatively charged. They have extra electrons. How do we know this? Well, we need something called formal charge. Formal charge is just a technique for kind of tracking where you've moved electrons. But basically it is the expected when neutral, so the neutral number, minus the actual formal charge electrons. Now, formal charge electron is a little bit different than octet. It's a similar idea with one rule that's different. For octets, we said, hey, a bond counts as 2 and a lone pair counts as 2. For formal charge, it's about the electrons that atom controls. A lone pair is absolutely controlled by that atom. There's nothing else using those electrons. So that oxygen sees 2, 4, 6 from its lone pairs, and it gets half of its bond. This is what's different about formal charge. Shared electrons, you only count half of them. And so that oxygen sees 7 formal charge electrons. Well, oxygen normally wants 6 when it's neutral. So 6 minus 7 is minus 1. It has a minus 1 charge. There are more electrons in control than it normally thinks it should have. And so why is that oxygen a minus? Well, because it has a little bit more electrons. If we do that for one of our bottom or top oxygens, well, 2, 4, but it only gets half from its bonds. Well, octet would have said 2 and 4 from the bonds, so 1 and 2. So there's 2 here, and 2 there for formal charge, which means this is 6 minus 6 for 0. We don't think of the bottom or the top oxygen as having charge as drawn because the amount of oxygen or electrons they are in charge of doesn't exceed what they expect. And so what we find is that the extra charges show up on the atoms where we put the extra electrons, which makes sense. That's where the extra electrons are. That's where the extra negative charge is. But what if I hadn't put those electrons there? What if I'd decided to put the extra electrons on the top or the bottom? If I'd done that, I would have gotten a shape that would have looked like single bond up and down, and a double bond left and right. And I would have found that my negatives were on the top and bottom. These are equivalent structures. I had the choice of the same atom, oxygen, to put those electrons on. So why pick one set versus the other? You don't. Well, we draw Lewis structures like this. This is a static, unmoving image, but electrons are waves. They are oscillating. The bonds are vibrating. The atoms are shaking and the molecule is rotating. Our flat, static 2D drawing cannot really represent what's happening. And this raises a problem because it isn't one or the other of these. It is actually a hybrid of the two. In fact, it's a hybrid of even more. We had more options. I could have done top and right, or I could have done bottom and right. I could have done bottom and left, or top and left. All the possible combinations of where we would have placed those two electrons, all of them play a role. And so this leads to what we call resonance structures. Let's take a slightly smaller molecule for this one. Let's look at CO3 with a 2 minus. I'd have a carbon, 4 electrons on it, an oxygen, and an oxygen. And you'd start with your 6 standard electrons on the oxygens. I have 2 negatives, so I'd get 2 extras. And then I'd pair anything that remains. So 1 from that oxygen still unpaired, 1 from that oxygen, 2 from that oxygen. I end up with a shape that is a double bond, a single bond, and a single bond, with 2 negatives. If instead I'd put that extra electron over here, I would have ended up with that bottom negative on the right. Well, there's another way to show that. The idea is we kind of fold things in. This lone pair could dive to attach to that carbon. We could say, hey, instead of sitting on the oxygen, let's bond to that carbon. Carbon cannot have more than 4 bonds. That would break its octet. So another bond has to move out of the way. If you move a single bond, you break the atom off. But if you move one of a double bond, you still connect the carbon and the oxygen. This is basically a Jacob's ladder style thing. It folds in one and the other folds out. The net result, though, is that we get a shape. How will that affect things? Well, that bottom left carbon now only has 2 lone pairs because the third one formed a double bond. that top oxygen didn't change. Nothing happened there. So it looks the same. And that right bottom oxygen, well, it still has the single bond, but the second bond broke and the 2 electrons just went out onto the oxygen. This will give us a negative on the bottom right oxygen. And this can happen again. We can say, hey, what if the top folds down? Well, it's going to force one of the multiple bonds to break away. And the net result of that will be that our carbon will now have a double bond going up, a single bond that didn't change going down and to the right, and now a single bond going down and to the left. Put our charges on it. Our charges will be on bottom. What we've done is drawn 3 different versions. Effectively, we said, hey, I put my extra electron on the top and the lower left, or I put my extra electron on the top and the lower right, or I put them both on the bottom too. And those are the only 3 possible combinations for how to put those extra electrons on at the start. This folding in mechanism, the take a lone pair, swing it in, break a double bond off. This is very handy for seeing all the possibilities. The basic rule is if you ever have a lone pair, so one lone pair, and that lone pair is 1 atom away from a double bond, or from a multiple bond, could be a triple. If you ever have that situation, then that lone pair can fold in and push out one of the multiple bonds. As a result, you'll get a new slightly different structure. And that slightly different structure, all that will have happened was that you moved the negative charge and the double bond. You said, hey, it used to be negative on the left, double bond on the right. We swapped that to double bond on the left, negative on the right. The real structure of carbonate is actually the hybrid of all of these. If you can go and measure, and you could look and you could say, hey, what's the distance between this oxygen and this carbon, and this carbon and this oxygen? Well, a double bond is shorter than a single bond. And so if it was one of these, we should see 2 carbon-oxygen bonds that are longer and one that is shorter. But the reality is we see 3 identical bonds. They're all a little shorter than a single, but a bit longer than a double. The real image, the real structure is the hybrid. But the problem is we can't draw that. There's no way to, in real time, draw moving things. It's too hard in the hand to draw that fast. And there's just no good way to show like a 1 1/3 bond. Lewis structures can't do it. And so these are resonance structures. They help us show the possible ways we could have drawn it, and then we have to tell ourselves, and we use the brackets on the side to say, hey, these are all the possibilities. It's the hybrid of them all. And that is the idea of a resonance structure. We see them pop up in many places, especially with ions.